some task about the technical drawing. So for sure, one question from those 6, 7, I'm not still sure how many, but at least 6 there will be questions, 6 to 8 probably. The one question will be from the drawing, from the lecture of Mr. Vujicic. All the other questions, so 7 probably, will be from the list. There are example questions also from Mr. Vujicic in this document. So in the materials for the exam, in this catalog on ePortal, you can find example questions for final test ET-doc, and there you will find some sample questions. Anything more about the formal stuff? Any more questions about the exam? Because next week we don't have. Again, a reminder: there is no lecture next week. So next week there you have an exam with Mr. Vujicic. So he's taking this term, and he's organizing his test. And we meet again in 2 weeks' time. So if you have any questions, let me know over email, or just ask me now or during today's meeting. So any questions from the formal side about the exam, about the lecture, about the test? The results of the test, maybe from my side, the results of the test will be sent automatically individually from JSOS. And the final mark, remember that the results from the test, from the exam, might be different than the final mark you will get in the system, because the final mark is the average from the lab and the lecture. So the lecture has slightly higher weight, but still it's optimistic version of the average. It's optimistic average, as I call it. So the final mark will be different. So the laboratory has the influence on the final mark, as it should. Good. So if you get to some question, let me know. So ask the questions, raise the hand during the lecture. If no, you can always write me an email. And if no questions, then we meet after this lecture. So we meet in 2 weeks during the final test. Okay, we finished. We finished here about the testing. So the main subject for today is testing and reliability of electronic devices. This is our last subject. First we have to finish the individual, the equipment for the testing. We spoke a bit about the parameters of the voltmeter, because this is the very basic measurement device that we must have. That it's a must actually in every lab. Every electronic lab, so that's excellent. That's the it's really a must it's really a must. Another device that I'm not able to that it's not possible to work to test anything, to start any electronic device, is that is a necessity in every lab, is the power supply. The power supply, regulated power supply, in fact. So not just a power supply, because you can have today, you can use USB charger to be your power supply. It does deliver 5 volts and a couple of watts today. But remember that it's not. So this is not something that you can rely on during normal daily practice. So in order to be serious in the lab, the good power supply is the element number 2. The element maybe number 3, because we must have some soldering gun, some soldering equipment. Second is the multimeter, more or less decent. And the third on our list of something that must be available in every lab is the power supply. What kind of a regulated power supply? By the way, regulated, because it's missing here. Regulated power supply. That's important. Regulated. power supply. So we must have something. So the problem with power supplies is that unfortunately the laboratory or the workshop power supplies, they're regulated in general. They are fairly expensive. Maybe not as expensive as oscilloscopes, but they are more expensive for sure than the soldering gun, than the first two positions on the list, so the soldering gun and the multimeter. These, in case of power supplies, why they are expensive? Because they are linear. Mainly, they are linear. For the so here on the slide, actually there is a switching power supply, but this actually for the, as our major power supply unit in the lab, we should rather avoid using switching power supplies. Of course, they are cheaper. Of course, they are smaller. They are lighter. That's good. But the power supply, the major power supply in our lab, should be linear because it should be perfectly clean, so that we don't fight with the power supply, we don't fight with noises coming from the power supply, but rather use it as our reference in case of voltage and in case of the current. Because what is important in case of power supplies is that we have for sure voltage adjustment. We have voltage adjustment, a knob or some possibility of voltage adjustment. The voltage in the laboratory conditions, it is good enough if we have 0 to 30. 24 is the minimum, actually. 24 is the minimum from my perspective, from my many years of experience here in this field. 0 to 30 is sometimes not sufficient, but for the start, 0 to 30 volt DC, of course, is something that we must have in our lab, at least 0 to 24. But the second thing is the current capability. So yeah, this picture that I took shows 30 amps, and no, actually we don't need that strong power supplies, and normal application is good enough if we can really, for normal laboratory conditions, for normal testing of various electronic devices, especially microcontroller based electronic devices. We need something around 2 amps, maybe 3 amps. If anything more than, if anything stronger than 3 amps, that's great, but doesn't have to be. So you don't need to go to 30 amps. So that's why switching power supply is really not necessary, unless you want to weld something, because really 30 amps is quite a lot of current, and very thick cables are necessary for delivering such a current, such a high current signal. So 0 to 3 amps is more than enough. And again, on this power supply, there is no direct regulation of the current, but the second knob here, instead of some whatever it is, noise offset, there should be a current limit, current limitation here, regulation of the current limit. That's very important as well. That's very important as well. Why is that so important? Because sometimes we are when we are not sure, especially when we are starting a new device, we are not sure, for example, if everything is mounted assembled properly, and then supplying it with unlimited current, with such a power, with unlimited power in general, means that something might evaporate, and not only you will break a component which was not soldered correctly, for example, capacitors with messed up polarization or polarity. So not only this capacitor will evaporate, but it will damage the board, because we don't care about the capacitor, so it's just a couple of cents, euro cents, so we can live with this. But the problem is if this burning of the capacitor and evaporation of this capacitor, how much will it damage the PCB? Because if it will damage, the costs will be much higher. Therefore, for the as a laboratory, so the standard procedure in for starting a new PCBs and new designs is to do it very cautiously, with the current being damped to some low values like 100 milliamps, then 200, 500, and so on. So I don't think that's a good idea to start with the maximum current allowed or without a current regulation. So that's why the good, proper regulated power supply again should be linear, should have current limitation or current regulation, and should have those ranges of voltages and currents, so 0 to 30 volts DC and 0 to 3 amps. That's good enough. Slightly lower values like 0 to 24 volt DC or 0 to 2 amps are good enough, but also higher values are welcome. A nice idea is to have multiple outputs, because there are such power supplies in the market as well with 2-3 outputs. For example, with dedicated 3.3 volts or dedicated 5 volts outputs and 2 regulated outputs. That's even better, but of course the price rises. So the very bare minimum is what you have here. Anything more than this is really welcomed. Then the next equipment that you can find in the lab, signal generator. Actually, not that important. Of course, it's not something that we don't need, because from time to time a signal generator is useful, but frankly, today with the existence of so many microcontrollers. So when we are starting a microcontroller, maybe this way, when we are starting a microcontroller unit, a microcontroller device, quite often we can use another microcontroller board to emulate some signal source. The more problematic is when you would like to construct something in radio range, so something that's sending or receiving some radio signals, then a generator might be more useful, but then not such a stupid generator as you can see here, that's capable of generating up to 1 megahertz of square wave or triangle wave, but then because this small generator is really not very peculiar, very useful, in my opinion, in majority of cases, but rather professional signal generators generating AM, FM, PM waves from within a single or multiple gigahertz range. So then such generators might be really much more useful than the stupid one that you have here. The problem is that such signal generators might usually cost the cost of such generators is about 10,000 euro and above, which means that in the amateur lab, signal generators are not really something that's realistic, because who can afford such a huge money for something that's useful from time to time. Another examples of the elements useful from time to time that you can find in electronic lab, but which is really not that first choice thing, is the pulse generator. Something quite. This pulse generator is of course for testing digital circuitry and for generating a stimuli to this to the input of this digital circuitry, so that we can then observe it on some logic analyzer. Actually, today pulse generators, again, we have so many so nice microcontroller boards available, then we can build such a pulse generator for a fraction of the price of the professional one. So unless you want to test multiple gigabit buses or even multiple gigabyte buses, then you don't need it. The pulse generator, a subversion or a very close sibling is digital pattern generator, but again, something you can find in the professional labs. For amateurs, not really important. Then frequency counter, again, an equipment, a testing equipment for checking the operation of electronic circuits, various electronic circuits. The frequency counter is actually quite it's a so-so equipment outside, so it's not in the first group of devices that I would need in the lab, but it's in the second group. So you can think for some applications a good frequency counting for high frequencies, because here on the slide is a 2.7 gigahertz frequency counter with 8 digits, so quite a decent resolution and quite a decent stability. So then you can think about it. Besides, it's quite cheap comparing to the, for example, to the good signal generator. The frequency counters even counting very high frequencies and with very good 0.01 ppm stability or even higher stabilities. They are available at a few €1,000 and less. So 1,000, 2,000 euros is the price. Of course, it's not for free. It's not for free, and for this reason, for simple applications, so unless you need so many zeros, so for simple applications where you just want to check the frequency, then we can use this. Of course, the excuse me. Of course, the multimeter, because the multimeter can be used for checking small frequencies with let's say decent resolution, because that's not a good resolution, but decent resolution. And of course, the ultimate thing for checking is the oscilloscope. So the oscilloscope is definitely it is a must in every lab. It is something that we must have in the laboratory. The problem that we have with the oscilloscope is, of course, the price. Yeah, that's not the oscilloscope. It's kind of a joke because it's an old-fashioned oscilloscope. Yeah, in the lab we should have something like this. So the oscilloscope with the digital one with multiple inputs and the bandwidth going into gigahertz region. The problem is, of course, the pricing, because the oscilloscopes start with quite low, so we can quite low. A low for the oscilloscope is 1K, 1K euro. That's the problem. So this is a low price for the oscilloscope. The oscilloscope with 1,000 euros. So in this price range, they can be multiple channels, so 2 to 4 channels. The problem is with those oscilloscopes that the displays are usually quite poor and quite small, sometimes black and white even, although for 1K you can buy a 4-channel color display oscilloscope. But usually the bandwidth is a problem. So here the number of samples per second is usually below 100 megasamples per second, which means that the signals, the bandwidth of the analog part of such oscilloscopes is within 20, sometimes 50 megahertz. So that's something you can expect from oscilloscopes from this price range. Of course, nothing really peculiar. So you can measure voltage, you can measure time, you can measure frequency, period. All this is the standard, but nothing really more about the such cheap oscilloscopes. Then we have the whole range of oscilloscopes, finishing something here, because this actually this oscilloscope from this picture is about 100 times, it's about 100K. That's the pricing of this oscilloscope. More or less it's in this price range. It's expensive actually. The standard pricing for a very good oscilloscopes is about is somewhere in the middle. So for 10 to 20K you can buy a very good oscilloscope. Okay, of course, for the amateur lab, that's unaffordable. So still the price is far too high. You can expect from such oscilloscopes, by the way. Of course, the price is very high, but this oscilloscope gives you the usually 1 gigahertz sample rate, gigasamples per second or above, which means that you can sample signals with 200, 300, or 500 megahertz even. And giving you also such nice things like the analysis of protocols, like the deep analysis of from the signals from the analog side and from the digital side, and from the digital side as well. So the good oscilloscope is a real friend of any electronic, and it did that when you start using the oscilloscope. actually the multimeters, the frequency counters, they become not so useful, of course, for some applications. It's easier to use a frequency counter and the multimeter, but the oscilloscope is really a must in every professional laboratory. In the amateur lab, if you are not able to afford this, maybe not very high price, but significant pricing. Then today you can find on the market USB scopes. You have various USB scopes on AliExpress, for example, in the price range of €100, so much lower. The scopes are limited in they are using our computer as a display quite often, so they are USB. You have to connect them by USB. Some of them have the HDMI output for autonomous display. And they are actually, because the pricing is much higher, much lower than the of professional oscilloscopes, then for the amateurs, for the beginners, such an oscilloscope is also it's also a realistic choice. So it's always better to have even this €100 or so USB scope that will show us the major signals that we have in our on our PCB, than to have nothing and be blind. The oscilloscope, even the cheapest one, is much better than having nothing, than just using the multimeter. So again, for major equipment in every lab of amateur electronic, these are soldering gun, multimeter, then power supply, and the oscilloscope. So with those four elements, of those four devices, you can start playing with, of course, a computer, PC computer, but everybody has a PC computer. I think that's quite obvious. So then you can start with, you can start making a decent PCB projects, analog and digital, with this equipment. Yeah, in case of such nice oscilloscopes, so the top values, so take a look, we are talking about tens, if not hundreds today, of gigasamples per second, with the deep analysis of various interfaces and so on. But again, for the sake of analog, or amateur, maybe not analog, but amateur laboratory, electronic laboratory, we don't need such a super highly sophisticated equipment. Much cheaper oscilloscope will do, but the oscilloscope really is an important, very important part of every laboratory. Okay, then we go from the analog, from the analog. From the amateur testing, we are going towards something more complex. A few words, because we just have today, so not too much time, about the factory testing of electronic devices. So for factory testing, naturally, there can be used such devices that we discussed from the just a moment before. So the oscilloscope, power supply, voltmeter, plus, because we are talking about factories, which means that the money is not such an issue. So then the device, such pattern generators or signal generators can be used in such manual testing. But in professional factories or in larger factories, the manual testing is not something that we are fond of, because it's expensive. Because there must be a human being, there must be an expert human being that is doing the test, that's performing the testing. That's why in factories, basically, we are going towards automatic testing, and there is a group of equipment called the automatic testing equipment that can be found in any more or less professional factory dealing with PCBs and dealing with electronic devices. So the automatic testing equipment is, of course, expensive to be constructed. It's expensive to be super, because it has to be supervised from time to time. but it's automated, which means that the operators, so the people actually that operate those devices can be paid less, because they don't have to be very specialized, and they don't have to really understand what the ATE is doing. They are just getting the results, so they are just taking the PCBs and or devices and connecting them to the ATE, and then pressing the button, and then green go good, red bad, and that's it. So the ATE is good for this, because of it. So of course it's expensive, but the tests are swift, and then no specialized people are necessary, skilled people, no skilled personnel, that's the correct word, no skilled personnel is necessary to perform the testing, which is actually very good. The ATE, the subject of automated testing equipment, is very broad, because each factory actually has something special. So there are some, let's say, categories that we can try to, that you have here in the slide, major categories of the testing equipment, but they're the number of versions equals almost to the number of factories performing such tests on the market. Let's just analyze some those major categories, and with some small examples. At least let's do this. Of course, no time to analyze every possibility that's here. So the main types we can of the automatic tested equipment, the main types that I find in the industry are five major types are placed here. So the first, PCB inspection systems, especially the automated optical inspection, also X-ray inspection here, automated. So automatic, so AOI and AXI, so two major subcategories of the PCB inspection systems. Though the inspection of the PCBs after production is still, you can still find factories where the PCB inspection is done manually, which means that there is a group of people that are just viewing the PCBs using kind of microscopes or let's say magnifying glasses, because they are professional there's professional equipment supporting this. The problem is that there are people that you have to be paid for this, and the people are today more expensive than good cameras, because we have plenty of good cameras today available in the market, and that's why because the price of the cameras dropped or is still dropping, that's why the automatic optical inspection becomes more and more common. Then we have the automated X-ray inspection, which means testing for hidden problems, especially with the assembly of BGA and LGA cases. So whenever there is no access to the soldering to the pads, because in BGA we have the pads under the chip itself. That's one of the places where the X-ray inspection and automated X-ray inspection, when there is a template how the board should look like, and then the equipment itself automatically makes a photo and compares the photo to the template, giving an information that the board is fine or the board should be reviewed then by a human being, because it's in the factory, it's working this way. And if there is any problem, still the human being comes in, a human being then and checks the board. Then we have the automatic equipment in the class of ICT, the class of in-circuit testing, which means that a human, usually an operator, takes a PCB or a device, then something like this, the device prepared with special testing pads, those then such excuse me, what's this? Excuse me, some too many things in the background. Okay, the going back. So in case of in-circuit testing, usually we have something like this: that there is a board, there is a device that have special connectors for testing, or just the pads. And the pads, then we have such as in-circuit testing, such devices. Large one usually, because the equipment itself, the site itself is very is usually takes some space with the various connectors. So like such things like here. So there are the probes. Take a look. Various probes are available for attaching to various testing points. Then on the ATE for testing, there has to be prepared first a template with the probes placed in the places where the PCB, where a PCB has the testing point. And in this in-circuit testing, when we touch, when there is a contact, then in the stimulus is then delivered from those large cabinets where there are various signal generators and pattern generators. All this programmable and controlled by some application. And then in this application, the operator just presses start, and then the ICT test starts, and the board is tested then automatically, and the board is tested then automatically. So this is in circuit testing. Then another automatic equipment. So with this in circuit testing, we can check out, for example, like things like the leakage or the continuity. And these are the things that are checked in with this method. If we want to check if everything is working properly in case of microcontrollers, of memories, and other digital circuitry, then this kind of automatic testing equipment is used. So the JTAG boundary scan testing. JTAG is the standard industrial protocol for testing. Actually, this is for testing of devices internally. So all the devices are made in a chain, because the all digital or JTAG support, all the chips that are supporting the JTAG testing during the design phase, we have to connect them in a chain, which means that we have all the devices in one chain, and there is just one connector for one connector where a special JTAG interface is being connected. And then we can test, through this JTAG testing, there is a possibility for the operator to connect to any digital device and to perform any internal test of a microcontroller, of a microprocessor, of an application processor, of a programmable logic, and of even smaller elements like a memory, because there are memories with JTAG connectors as well. So the ICT test is for testing usually the electrical connections and the analog part. While the JTAG boundary scan testing, this is for testing the if everything operates properly, but seen from the internals. So seen from the internals of the silicon of the chip itself. And then we have a similar thing to ICT actually, but a bit different, on a bit higher level, because ICT is for testing bare testing of connections usually, and for testing of if the components are properly assembled on the PCB. While then we have the so-called functional testing. So this is on a higher level. So Again, the PCB is the lowest level, then ICT a bit higher, then JTAG is the functioning of the PCB itself, and the functional testing is on the top of it, because the functional testing, so three possibilities here. So the functional automatic testing equipment, rack and stack test equipment through the GPIB interface, and then chassis or rack based test equipment here. But this is for testing if the device functions properly after the assembly. So for example, in the factory, we are having, there is a factory which assembles the, I don't know, smartphones maybe, and this functional testing is about testing if the display is operating properly, USB connector, I don't know, the speaker, the camera. So this is the testing on this level. This is a testing on this level, if everything works properly. Naturally, there might be a combination of all the above. So when we have this kind of equipment and this kind of connectors, we can at the same time check the connection, so make the ICT test and make the JTAG boundary scanning as well, because that's not a problem to connect, for example, here, to use those pins for connecting to JTAG. There are 5 pins, 5 or 6 pins in JTAG, depending which actually pins are used, and to connect to JTAG test, to JTAG chain, and then perform this JTAG testing of our PCB. That's something we are doing in factories. Of course, it can be very complex. Take a look. There's cabling, possible cabling on the various test sites. So what is hidden underneath? So something you can expect. You can expect from here. So there are just 2 cabinets shown, but what is behind those cabinets? How many cables are there? Are there so many cables as seen here? It's possible. So it really depends on the factories. It really depends on the on the particular realization of this ATE. But in all factories, again, in all factories dealing with electronic devices, dealing with starting with production, the ATE and some site for testing plays a crucial role, because it is, of course, thanks to this site, we can deliver the equipment functioning to the final user. In the standard factories, because of course you could ask, because theoretically 100% of the devices should be faultless, and in 100%, if there would be the case that 100% of the devices is faultless, then no testing would be necessary. In normal factories, then the problems are about 3% of the devices. So 97% of the devices is faultless and can be delivered to the user, but the 3%, usually that's a good number. Actually, if there is more than 3%, then something is wrong. If there is less than 3%, it's also something wrong, because it means that maybe the testing is not proper. If there is more than 10%, there is some problem with production. So that's how it looks from the practical point of view. Yeah, and okay, that's about the production. So for the production, we finish on the production with functional testing. So with the testing on this level, we are finishing in the factory on the production line. Yet, especially when we're performing some development and doing some and developing our designing or redesigning our device, so doing a design and redesign of a device, we need more than just functional testing. Okay, during the design, so then we go a bit higher compared to what we were talking up to now. So the functional test is the level. It was the top level in the factories, because during normal production, after functional tests, the device is wrapped up in a package and shipped to a shop or to a magazine. But when we are doing a development or design, then the functional test is only the starting point for something more sophisticated. The more sophisticated test in the R&D department, because the design and development, for design and development in every factory, there is responsible some research and development. This is so-called R&D. So this is, we can call those tests R&D tests. So to talk about them differently from the production tests that were discussed today, that have been under discussion thus far. So the R&D test can be split again into a few categories, into many categories, but just to make it simpler to understand and to remember, I split this R&D test into 4 major categories. So the functional test, because even during R&D, during the development, we still need to check out if our device operates properly. Yet the functional test, there is a difference in the R&D functional test and the production functional test. In the production functional test, we are interested because everything is working, and during the R&D phase, during the production. First of all, during the production, the functional test must not take too long. So the functional test must be as fast as possible, because time is money during the production. During R&D, the designer, the developer usually wants to see more. Therefore, the functional tests in the R&D part are way more extensive. Way more expensive as well, but they are way more extensive and much more sophisticated usually than during the production phase, because the functional tests during the production are just a small subset of the functional tests performed during the R&D. And so the functional testing normally we call it a quality assurance process. So this is something, the FT test is about testing the whole functionality of the device, the whole functionality. So here we are testing, or during the R&D functional test, all the functionality, complete functionality, maybe in other words, of the device is being tested, or should be tested, or should be tested. So the steps during the functional test, R&D again, so during this part of functional test, is first we should identify the expected functionality, so the functionality that we want to be tested. Then we create the data pool for this functionality that we want to test. Then we determine what should be the output. So when we what kind of output we expect from the input, from the input data. Only then we make the execution and we compare and analyze the received results. So these are the steps of the functional testing. The functionality that is to be tested really depends on the device that you want to test, and on the time that we have. But here, in case of R&D functional testing, or functional testing in the R&D department, much more time is available, because the testing is really very important part of every design process, and quite often it's more difficult part than the design itself. Especially that the functional test is not the only test which are required before approval of the project, and the other tests, the other categories, so the reliability, the ESD and EMC testing, about those 3 categories of the test performed during the approval process of our device. About those tests we'll talk only after the break. So let's now have a quarter of an hour of a break, and then we'll get back to this subject. Still have a minute, so let's wait for everybody to synchronize. Okay, So let's go back to our test procedures during the R&D phase. So second thing, reliability test. Reliability test, in case of reliability tests, so it's about, of course, as the name suggests, it's a group of tests. It's a group of various measurements for checking how our device how reliable our device is, our design, how well it works. From a practical point of view, so there are plenty of tests that could be placed here, chemical even, and physical and chemical actually. Yet, in my opinion, the most important here is first of all vibration and shock test. Second of all, the environmental reliability test. These are in case of vibration and shock, it's about testing if everything is assembled properly, if everything is designed properly, because this is for R&D. So if everything is designed properly, and if everything, in other words, if our device doesn't break out, doesn't break up during normal operation, during day-to-day use or everyday use. So that's about vibration. So various frequencies and various amplitudes here can be applied, as well. The shock testing. Shock testing is all in all stamping on this or throwing it against the wall so that the device survives it. So it really depends on what of what we're testing. So a glass laser will not be tested, will be tested differently than some connector or some military device. Anyway, this kind of testing is, in my opinion, very important. From the developer's point of view, from designer's point of view. So if our device is really can really survive a day-to-day use. Second thing is the environmental testing. So this is usually done in special climatic chambers. For the environmental testing, the devices are put under the stress of various temperatures and various humidity. Sometimes the various pressures. So it really depends what we are testing and what we want to check and what needs to be checked in our device, because of course it's going to be different if our device is to work in the free space, so be part of some satellite, or if our device is to be the part of a submarine or whatever. So the environmental reliability test, really important test, really important kind of testing for reliability in the reliability group. The other test, so let's say, so again, many more I could think about, but these tests are not really that important. So those two definitely the most important in the category. So other tests even less important. So gas corrosion test, soul spray test, X-ray fluoroscopic examination, and so on. So ion migration test. Plenty of things we could test here, but frankly, not that critical. Okay, let's go further. The fourth group that I think is important during R&D phase during the development of any new device are the testing for the protection against the ESD, so electrostatic discharge. So if our device, again, this is kind of a reliability test, but it's a broader category. That's why it's not placed into these. I didn't place it into the reliability test category, but as a separate test, because this category is very broad, very wide. So we have because the ESD, so electrostatic discharge, is a very common phenomenon. You know, each of us charges up to a few kilovolts. So especially when we are wearing proper materials, especially the not from for example, rubber sole is if we have shoes with rubber sole, and then we can charge up to very high voltages, and then if we are charged, then we can discharge. So this is happening each of you has met this phenomena in their life, in its life, because it's very common. Of course, if there is a spark, so this small bite when you're when you are close, where placing your hand close to a metal rail or to another human being, then it stings you just a bit, and it's not very painful. But if you can feel it, it means that it was 4, 5, 6 kilovolts. This kind of you were charged to this voltage, and it will do no harm to a metal rail on the stairs, or to a car chassis, or to another human being, but it will damage a microprocessor. It will damage the sensitive amplifier. So that's why the ESD discharge, the protection of the circuits, is a piece of art. It's a piece of electronic art. So maybe during, hopefully, I would say this way, hopefully during the further part of your electronic education, you will find this on some course, extended a bit, this problem of ESD, this problem of how to construct the electronic devices that are ESD protected, that they are they are not susceptible to the ESD electrostatic discharge. So today, fortunately, many chips are ESD protected by design. So there are special, because the simplest protection is the clamping diode. Is a clamping diode at each input of a chip. But the chips, the protection of the chips is a good part, it's a good thing, but we are using multiple chips in our device, and besides, not all the chips are protected in a similarly effective way, because for example, the diodes, especially the high frequency chips, are problematic from practical point of view, because those diodes, protecting clamping diodes, in order to work properly, they have to be constructed in such a way that they introduce high parasitic capacitance. So a couple of picofarads of parasitic capacitance makes no problem at audio frequencies, or even at microcontroller frequencies, but it's very problematic if you want to go to a couple of gigahertz. Then this couple of picofarads poses a lot of problems, and then we have to think about other ESD protection. So anyway, the ESD protection, so electrostatic discharge, has to be tested. So there are special laboratories, there are special equipment, there are special, in other words, in electronic workshop, we should be wearing special coats, we should be wearing special shoes, we should be wearing special caps, gloves, so that we don't charge up to high values, so that we don't break we don't break the device even before it's assembled completely. But that would take us another lecture to analyze all those things, all those requirements for the ESD protection. For now, so yeah, here is an example how the protection should look like. So we should have normally in the lab there should be a floor, a tiled floor, definitely not a wooden one, and not a plastic one. So there should be some floor tiles, at best some anti-static floor tiles. Then we should have a grounded wrist strap, grounded wrist strap. Everything shall be performed, so all the electronic operations shall be performed on anti-static table. On metal table it should be, with anti-static map on top. We should have anti-static tweezers, we should have the anti-static finger cuts, there should be anti-static carrier tape, anti-static bag. So as you can see, plenty of elements. Of course, we should see there is a anti-static coat here, because it's a especially woven from special materials. As well, there is a chair, so the lady or a guy here sits on a special anti-static chair. So all this is a standard equipment that can be found in any lab. From the amateur point of view, From the amateur point of view, it's really enough to have a metal table, a table connected to the earth, the table which you can touch before playing with a PCB. That's from practical point of view. So the ESD, so that you can discharge somewhere. So of course this protection is very extensive, that you can see on the slide, with plenty of elements, because this is for production, and the electronic chips are quite sensitive to the ESD. But in the amateur conditions, in the amateur laboratory, fortunately, we don't need that many protection mechanisms. Again, from my point of view, so again, from my practice, that's enough to have something metal, grounded metal around, so that before you touch any electronic devices, before you get nearer to the electronic devices, either with a tweezer or with a soldering gun or with a measurement probe, then first you discharge yourself, you discharge your body and your hands with by touching, first some grounded metal part, and that's from practical point of view good enough. In case of ESD protection tests, this is a wide category as mentioned. So we have various tests available. There are extensive norms describing, and plenty of laboratories doing the tests, performing those tests. Even here at the Wrocław University of Technology, there is a special lab. Of course, right now you are mostly at your homes, but when you come back at the university, you'll see the cube building, a side of the between C3 and C4. This is the building where the lab for ESD test is available, is present. So there is a special lab just for the ESD and the next type of EMC testing. Because from the tests of ESD, by the way, the simplest way of testing the ESD is the simulation of a human being. Of course, nobody will use a human being and charge and discharge a human being, but there are special guns. There are special guns that are charging to a few kilovolts, and the simplest test for ESD protection is to shot with this gun to our device, to various parts of our device, like connectors, like displays, like case, and then during the test, the operator shots with the gun to a device, shots with a single pulse or a pulse train with a few kilovolts, and if the device survives, then it's protected as well. It's properly designed against the ESD. If something breaks inside, then we have an information during R&D. As an R&D department, we have an information case. Something has to be protected better because it did not survive the test themselves. So the funny thing is here that it's just about having a gun, a special ESD gun for testing, and the tests are mostly about it. More difficult testing is in this category, because ESD is one part of the problem. Another part of the another important subcategory or category for testing during R&D phase is the EMC. EMC stands for the electromagnetic compatibility. So these are the testing. So this lab I mentioned just a few minutes ago. This lab is about the ESD and about the EMC as well. So both kinds of tests are performed there. The EMC is more complex. It's more sophisticated. It's more difficult to be performed. What the EMC is about, and why is it so important to test a device, an electronic device, about the EMC, about the electromagnetic compatibility. To make it short, the EMC is about proper coexistence of various devices within the environment. You know, the electromagnetic spectrum is limited. We have a lot of frequencies, so there is theoretically a lot of space in the EMC environment, but in fact, the electromagnetic spectrum is very well defined and very strictly defined, and there is no and very strictly regulated, maybe not defined, but it's very strictly regulated. And the most important thing about the EMC is that the devices, in order to coexist with each other, in order to function properly, they first of all must do no harm to other devices, so they must not emit extensive electromagnetic radiation. And at the same time, they should not be, because must is in the first category, but the second thing is they should not be sensitive to even strong fields, electromagnetic fields coming from the environment. So first thing is a must, because during EMC testing there are special norms against, for example, in Europe we have the CE marking. The CE marking, there is a couple of things the CE marking means. Each country has its own, by the way, its own compatibility marking. In Europe, it's C, and one of the elements of the C is if the device is compatible electromagnetically. So if, in general, if it does not emit any radiation which might be harmful to other devices, So the EMC, of course, from the R&D point of view, the importance is in both directions. So it is important from the designer's point of view, if the device emits something, and if it is susceptible or sensitive to some radiation from the external. But from the regulatory point of view and from the consumer's point of view, the importance, much more important, is if the device is quiet, electromagnetically quiet, so if it does not emit anything from to the external world. Yeah, what happens if there are if the EMC norms are exceeded, if our device goes beyond the regulations, then various interferences may happen. And yeah, I do remember when I was a kid, we were using a motorbike, and we were riding it quite a lot. The problem is that this motorbike was very EMC incompatible, and whenever we were traveling across our village on TV screens, the TV screens were going wild. Because there was a huge interference between the EMC field, the electromagnetic field emitted by this moped or motorbike, and the TV received by the by TV set. Of course, there are many more things happening possible, so you can read this, you can read them here. Some examples of the radio interference with radio reception and with radio transmitters. As well, the interference from transients is something that's still happens. So this moped example is the interference from transients, because the transients coming from very fast switching of high voltage signals, because usually the transients that the most harmful are from switching of high current or high voltage signals. High currents and high voltage, so very commonly, is in the welding during the welding equipment. So this is if you have a welder, especially of the older kind, somewhere in your garage, then you can test with this welder. You can start using the welder, and at the same time you can start using computer nearby, and you can check out if the computer is susceptible to the interference coming from transients from the welder. It's one of the example. Another source of problems in case of transients are various kinds of high power motors. The motors are as well a lot of transients and a lot of EM fields, EM electromagnetic problems coming from that. In case of the EMC test, they are split into two subcategories. So the emissions conducted and the emissions radiated. These are the two major categories, because we may have a situations where our welder, if we talk about it, the radiates these problems, these transients switching is being conducted through the cable and through the AC mains sockets to other devices, and even on the second side of the building. At the same time, the same welder can radiate the RF field because during welding there is also a switching of high current. That's why that's the problem. Slightly connected is the fourth category, but again, these are two most important. The LF power disturbances, let's say, it's usually far less critical. Although still it is tested, still there are norms and regulations against it. Then we are testing against immunity, but as mentioned, emissions are way more important because they are regulated. First of all, no harm. Then, if our devices poses no problem to the environment, then we can test it, and plenty of tests are defined for testing the immunity of our devices against conducted RF, against radiated RF, against voltage dips, magnetic peaks, electrostatic discharge, fast transient surges of voltages. So surges, for example, is protection. So if tests of surges are for protecting against thunderbolts, because this is the main source of surges in practice. So if we want to test, if we want our device to be thunderbolt and thunderstorm insensitive, if we want to check it, then we need to perform this immunity surges test to see this and to check this out. So these are the tests. These are the types of tests that we are doing. As you have seen, in case of the test procedures from a lot of things to test, a lot of possibilities we have, and so many possibilities because there are so many factors influencing the operation of a device, and all the results from all those tests, from all those categories, are really precious in real life, and are really precious during the development process. And that's the reason why that I mentioned already, that quite often testing is much more difficult than the development itself. It's much more difficult because, from my opinion as well, it's much boring, to be frank. Performing so many tasks, which is really required. Real life consumes a lot of time and energy, and forward it's in the development stage.
Excuse me,
Professor. That's also the problem from practical side.
Excuse me, one second.
Yeah.
Could you repeat the last part? I couldn't hear it. I think your or my internet cut out. Sorry for interrupting.
We don't have a time. It is all recorded, so it will be placed. On ePortal. The recording itself.
Okay.
So you will have a chance to listen it, re-listen it, or listen it at home. This part, because we have to move forward. We have just 20 minutes left, and there's one more subject to go. Yeah. So change of decoration. Change of decoration. Give me a moment. Please give me a moment. Okay. Okay. So we go further. The advanced issues. In case of advanced issues, 3 subjects, but we don't have enough time for everything, probably, and I don't want to make a slideshow out of it. So yeah, you will find the reliability and IPC standards, because probably we'll not analyze them. You will find them in from our curiosity. Summing it up again, because I think I have some problems. There's some problem with internet. But if you miss something about the connection, then everything will be is recorded. So you will be able to rewind the recording and fill in the missing gaps. So summing up, product development stages of all the electronic devices can be classified into 7 points. So first thing, with the conception of the product. So first of all, there must be a group of people or a human being that has an idea what is missing on the market, what is missing on the market, how a product should look like, how it should function, what operation should it perform. This is the phase number 1. So the concept creation, product concept creation. Then we have to check this concept. We have to prove that our product, that our idea has a sense, so that this is viable, so that it's going to operate. And the proof of concept means that we have to do at least some simulations. For sure, we have to do some calculations, we have to do some basic design. Sometimes in case of development of electronic products, sometimes we have to build something, or we are building, because we don't have to during proof of concept, but sometimes we are constructing something or building something, but we are not building during this proof of concept a complete device. During proof of concept, it is enough to construct and prove the operation of the most difficult and problematic part. So, for example, we are designing some new sensor, some new device for, I don't know, for face recognition. And in this device, we intend to use a new sensor, new camera sensor, very fast one or very accurate one or whatever it is. So but we intend to use proven algorithms. I don't know, developed by our company or by some our friends, or delivered online on some website. So if that's the case, then during the proof of concept phase, we don't need to construct parts, so this new part. So in this example, we would need to construct as soon as possible the new sensor, so the new camera with the new camera setup, proving that the new camera will deliver the information as intended, with the quality and bit rate and the level of details as intended. This is the proof of concept stage. So we don't need to make a complete device. The complete device is constructed in phase 3. So during this electronic device development stage. So in this stage, as the name suggests, a complete device is to be developed. This is the stage that usually takes quite a lot of time and quite a lot of effort, although it's not always more difficult than stage number 2, because proof of concept means developing something new, while the electronic device development, it's about developing something new, but it's a, let's say, technical thing. Technical thing, as I was trying to prove you throughout the whole semester, technical doesn't mean simple, because the process of choosing even such stupid thing as connectors, cables, case might certain parts of our device. So the electronic device development also means